To really test that we understand each of these different algorithms and that we're capable of explaining them to someone who has no idea what we're talking about, we're going to practice using each algorithm on numbers that are not base 10. We're going to start by making something called an addition table. And we're going to maybe practice in base 5. To make an addition table, we're going to look at all of the single-digit numbers in base 5. Those are the numbers 0, 1, 2, 3, and 4. We have 5 single-digit numbers in base 5. And we're going to practice adding all of the single-digit numbers. So we're going to make an addition table, and it's going to look a lot like a multiplication table, maybe that you've made in the past. We're going to put all the possible digits along the top row, so 0, 1, 2, 3, 4, and then all of the single digits along the first column. And we're going to look at adding all possible combinations. For example, 2 plus 3 would go in this entry right here. So we're going to complete this table, that way we can refer back to it when we are adding in base 5. Now remember that the way base 5 numbers work is that we have our singles, and instead of groups of 10, we have groups of 5. So for example, if I had the number 33, that would look like 3 groups of 5 and 3 singles. If I had the numeral 1, 2, that's not 12, that would look like 1 group of 5 and 2 singles. In base 10, that looks like the number 7, but in base 5, that same value is represented by 1, 2, base 5. We're going to go through and add 0 to each one of the digits. And I'm going to represent the digits using tally marks. So 0, I'm actually going to put a box to represent that there's no tally marks in the box, it's empty. For 1, a single tally mark. For 2, 2 tally marks. 3 for 3 tally marks. And 4 tally marks to represent the digit 4. So we have all of our digits, 0, 1, 2, 3, 4, all listed out here. And we're adding 0 to each one of them. Remember that 0 is the additive identity, meaning that when we add 0 to a number, it does not change the identity of that number. So 0 added to 0, that's still 0. 0 added to 1, that becomes 1. 0 added to 2, that becomes 2. 0 added to 3 stays 3, and 0 added to 4 stays 4. We can enter all of those in the first row. So we have 0, 1, 2, 3, 4. And then because we know that addition is commutative, we could have reversed the order that we're adding these. So we could have added 4 plus 0, and we'd still get 4, meaning that if I did 4 plus 0, the entry that belongs right here would look exactly like the entry that came from 0 plus 4. So I can copy all of these over. Next, I'm going to adjust this. Instead of doing 0 plus each of the digits, we're going to look at adding 1 plus each of the digits. 1 plus 0 is still 0. 1 plus 1, sorry, 1 plus 0 is not 0. 1 plus 0 is 1. 1 plus 1 would become 2. 1 plus 2 would become 3. 1 plus 3 would become 4. Notice that each of these sums has not had enough to regroup, but when we get to 1 plus 4, that is enough to make a group of 5. So we would represent this as one group of 5 with 0 singles. That number looks like 1, 0, base 5. Remember, that's not 10, that's 1, 0, base 5. Now all of these sums will fill into that second row, so 1 plus 1 was 2. 1 plus 2 was 3. 1 plus 3 is 4. And 1 plus 4, don't say 5, it's 1, 0, base 5. And because addition is commutative, we could copy the second row into the second column. So 1, 2, 3, 4, 1, 0, base 5. Now we're going to go through this process with adding 2 to each of our digits. So we'll have 2 tally marks plus 0, 2 tally marks plus 1, 2 tally marks plus 2, and so on. 2 plus 0 is still 2. 2 plus 1 becomes 3. 2 plus 2 becomes 4. 2 plus 3 is enough to make a group of 5, so that would look like 1, 0, base 5. And then 2 plus 4 is enough to make one group of 5 with one single. So that would look like 1, 1, base 5. And then we can copy these into our table. 2 plus 2, we said was 4. 2 plus 3, we said was 1, 0, base 5. And then 2 plus 4 is 1, 1, base 5. And we can copy those in using the commutative property of addition. Next, we'll move on to 3 plus each of our digits. And I'll represent 3 in each case with 3 tally marks. 3 plus 0 is 3. 3 plus 1 is 4. 3 plus 2 is enough to make a group of 5. 3 plus 3 is enough to make one group of 5 with one single. And then 3 plus 4 is enough to make one group of 5 with two singles. Copying that into our table, we have 3 plus 3 is 1, 1, base 5. 3 plus 4 is 1, 2, base 5. And we can copy 3 plus 4 is the same thing as 4 plus 3. We have one entry left, and that comes from adding 4 to each of our digits. I'll use 4 tally marks to represent 4. Notice that the only entry that's going to change our table is the 4 plus 4 entry. That's this last sum. 4 plus 4 is enough to make one group of 5 with 3 singles left over. So that would look like 1, 3, and base 5. So we have our table complete, and now we can read it. So anytime we need to add two single-digit numbers, we don't have to have these facts memorized, because let's face it, most of us will not memorize these. It's not useful enough for us to use our memory on that. So instead, we're just going to refer quickly to the table whenever we're adding single-digit numbers. Let's try some problems. If I wanted to add the numbers 3, 2, base 5, plus 1, 4, base 5. Remember, this is not 32 and 14. This is 3, 2, base 5. 3, 2, base 5 looks like 3 groups of 5 with 2 singles. And then 1, 4, base 5 looks like one group of 5 with 4 singles. Looking at the tally marks, we can see that we're going to have to regroup. Just in the ones place, we can see that 2 units plus 4 units is going to require us to regroup. But we could also see that just by looking in our table. 2 plus 4 is where row 2 matches up with column 4. That's 1, 1, base 5. I'm going to use the expanded algorithm here to say 2 plus 4 in base 5 looks like 1, 1, base 5. I'll spread those out. 1, 1, base 5. And then we can move on to the next column. In this case, we're looking at 3 plus 1, which is also looked at as 3, 0 plus 1, 0, base 5. Really, adding 3, 0 and 1, 0 looks a lot like 3 plus 1 and then a 0 tacked onto it. So we're going to look at our table for 3 plus 1. Find that intersection. 4. So 3, 0 plus 1, 0 and base 5 becomes 4, 0, base 5. And then we can add these together. 1 plus 0 is 1, 1 plus 4 is 1, 0 in base 5. So the number 3, 2, base 5, plus 1, 4, base 5 is equal to 1, 0, 1, base 5. And we use the expanded algorithm to show that. Let me show you how to do this with the lattice algorithm, maybe with a larger number. Let's add some bigger numbers like 1, 3, 2, 4, base 5, and 2, 3, 1, 4, base 5. To set this up for lattice, I'm going to stack the numbers vertically and I'm going to give them ample space between each digit because I know that setting up the lattice for lattice addition requires a lot of space. I'm going to draw my lattice under each place value. And now I'm ready to do my additions within each place value. 4 plus 4, reading my table, I can see that looks like 1, 3, base 5. That's 3 singles and 1 group of 5. 2 plus 1 looks like 3. That's 0 groups and 3 singles. 3 plus 3 looks like 1, 1, base 5. That's 1 single, 1 group of 5. And then 1 plus 2 is 3. That's 3 singles, 0 groups of 5. The lattice has been filled in completely, so now we can add down the diagonals. We get 3 in the units place, 4 in the groups of 5, 1 in the 5 groups of 5, and then 4 in the 5 groups of 5 groups of 5. So our final answer would look like 4, 1, 4, 3, base 5. Now, if you try to do these kinds of problems using the standard algorithm, I can almost guarantee that you will make a small mistake, if not multiple small mistakes, because our brain will automatically divert back to base 10, and we'll start thinking of numbers in base 10, and we'll write numbers that don't even exist in base 5. For example, 4 plus 4, your immediate thought is probably that it equals 8, but not in base 5 it doesn't. 4 plus 4 equals 1, 3 in base 5. So I write the 3 down here and carry the 1. Then I'll add 1 plus 2 plus 1, that's 4. No carrying needed here. And then I'll move on to the next place value. 3 plus 3 in base 10, that is 6, but we're not in base 10, we're in base 5. So 3 plus 3 in base 5 looks like 1, 1. So I leave the 1, carry the group of 10, and then I add 1 plus 1 plus 2, which is equal to 4. So I would get the same answer, but there's so many mistakes that can be made just because this is so brand new to us that it's possible that you might get it wrong just by using the standard algorithm.